So I've shared this notebook with everybody. Yeah, so I'll keep sharing it once every few days, I guess. Okay, so let us have a look at what we have been observing till now. So we basically took the finite potential well, whose height is u naught, and we put 0 here. Now when we solve the time independent Schrodinger's equation, we know that there's going to be at least one solution whose eigenvalue is somewhere below this, right? So maybe this could be your E1. At least one will be there. There could be more. And how we solve for that? We have to solve numerically only. And generally, this is where every textbook will leave you, right? So they'll leave you at this. But actually, there is something more interesting happening. If the energy of the incoming particle is larger than this, then this will act as a scatterer. So those are your continuum states. Okay? So you have continuum states. This concept is generally not presented in most of the textbooks, but it's very important, right? So these above this will be continuum, below this will be trapped states. And we solved for the trapped states last time. These are discrete. Okay, that means there is only a finite number of states. There cannot be infinite. There has to be a finite number of trapped states. And the lesser the potential barrier, U naught, the lesser the number of states generally. But in any case, there's always going to be at least one, no matter how small the U naught is. Also, the width of the well, this parameter, also makes a difference. So if that is quite wide or it is quite low, then depending on that, the number of possible states can change. But again, always one, right? Remember, never forget that. So this is one thing we learned. The second thing we learned, how do we solve for that? We got an equation A into tan of something equal to D into something else, right? So we can once, and this, there was K, there was kappa, all these equations was there. Once we solved this, we got a relationship between, we know what is the solution for E, right? E1, for example. Then we can substitute that into these terms, and you can express D as A times some constant. Okay. Once we do that, now our final wave function, phi of x, can be now expressed as A into e to the power minus kappa x, and into some constant here, right? And then A into e to the power plus jkx plus A into sine of or cos for the even state. For the even state, it will be A into cos of k times x, small k, and again some other constant, some c1, right? Some constant. This is the same constant, obviously, e to the power plus kappa x, like this. Okay, where you also know the value of k and kappa, right? They will be completely determined, because when we solve for E1, then remember K1 is root of 2m e by h bar square, right? 1 by 2, right? So this will be known, this will be known, this will be known. It will be a number. It will be some. It will be known. It will only be a function of x. All these coefficients will be known in terms of the energy E1. Then C1, this constant also will be known. Only unknown will be this A. How do we get that A? That A we get by, if you do integrate this from minus infinity to infinity, this must be 1, right? So when you do this, then that's how you can solve for this A. And once you solve for that A, you have everything. You have pretty much, you have the entire wave function completely specified. And so for each value of E1, there will be a corresponding phi1 of x, eigen function, right? E2 will have a corresponding phi2 of x, like that. Okay, so I hope it's clear to you how we solve. But generally, this wave function itself is less important than getting this E1 and E2 values. Those are more important usually. Okay, those will be more important. Right now, if I in real devices, our trap states and so on will generally be three-dimensional problems, right? In surface, if you do surface physics, then you have surface states. But I hope you got the idea. Okay, any trap state calculation, how do we do it? We have to basically solve for the Schrodinger's equation, and then we'll get some equation in terms. Then we get some equation that the this for this particular case we got this kind of equation, right? But what is this in general? It is actually an equation for the energy eigenvalues, right? So these are basically eigenvalue equations. You're going to get some kind of an eigenvalue equation. You may not be in such a simple form. If you take some general structure, may not come in such a simple form, but there will be some energy eigenvalue equations. This is what we solve first. So if you see quantum espresso, some very complicated quantum simulators, this is all they're doing. First thing what they're doing is they're solving for the eigenvalues. Once they solve for the eigenvalues, then you can go back and do normalization of the wave function, and you can they'll also allow you to plot the these probability distributions of the particular wave function as well. So this is exactly the procedure that complicated softwares do for more complicated configurations. This could be in three-dimensional space if you're doing, for example, solving for the exact energy eigenvalues for a quantum dot, for example. Why? Because right now you have quantum dot LED TVs, right? Or you have quantum dot LEDs, quantum dot photodetectors. So let's say you are working in a research, you're working on quantum dot photodetectors. There you are very interested in seeing how the eigenvalue spectrum, eigenvalue spectrum for that particular dot is. Because you want to design it for a particular wavelength, right? So you have to tune the geometry. You want to see how sensitive it is. If I change the shape, how much will the energy? All these things will come. But what is it? It's just an extension of the same idea. What we have done in 1D, more complicated research devices, they'll explore in 3D. And so you have to use numerical software to do these kind of procedures. Okay, but philosophically, that is exactly what they're doing. They're finding the energy eigenvalues, and in some case, there may be degeneracy between eigenenergies also. So there could be degenerate states which have the same eigenenergy. All those interesting things happen when you go from one dimension to a higher dimension. But yeah, philosophically, it's the same, right? And for example, there are a lot of interesting device situations where the surface becomes very important in research, right? So let's say you're making an LED, or you're making a laser diode, or you're making a photodetector, or you're making a very good transistor. The surface becomes very important. So what happens at the surface? So surface, what happens? If we will actually go solve the Schrodinger's equation for on the surface. So those are called surface. Those are whatever we have done right now. Extension of that to a two-dimensional case will give you all kinds of surface physics. And there also we expect similar kind of things. There will be trapped surface states, and there will be propagating surface states. They'll be confined to the surface. That's why we call them surface states. There'll be trapped surface states, and the trapped surface states will have their own energy eigenvalues, and so on and so forth. Okay. Right. So that is extension of this idea to two dimensions and three.
The sound is not coming.
Sir, you are not audible.
Even you people are not able to hear, sir?
No.
Okay.
Yeah, can you hear me now?
Yes, sir.
When did it get cut off?
So just 2 minutes back.
Just 2 minutes ago, so that should not be a problem. Yeah, can you see the screen?
Yes, sir.
Okay, so we will go to the next problem, which is tunneling by a finite barrier. So remember, in any Schrodinger's equation problem, the first thing you should ask is what is the shape of the potential? And so let me specify the shape of the potential first. It's a rectangular potential barrier. In this way, it's one dimensional. And let us again put 0 as the center of the barrier. So this is going to be minus a by 2 is going to be a by 2. And this is our 0 reference for the energy. And we only consider energies that are above this, above 0, only positive energies. I'll come to that later, but yeah, energies comes later, right? First, just the potential. And the height of the potential barrier is u naught. Okay, so before going into the solution, let us actually think about what is happening here. So if an electron comes in, it has some energy, or let's say physically, it's imagine a ball, right? So a ball comes in. If it has kinetic energy less than u naught, we don't expect it to be able to climb the hill, right? So you can imagine physically what is happening, right? Imagine a hill like that, where the height of the hill is u naught, and there is a ball that is rolling. The ball that is rolling here, it has some kinetic energy, and if its kinetic energy is half mv square, obviously, right? So if it is kinetic energy is large enough, then it will roll up the hill, reach the top peak of the hill, then it will roll down, right? So this we are familiar with. This is your classical equivalent of a hill climbing problem. So we want to do essentially the same thing. We want to send in an electron whose kinetic energy or whose total energy, you can think about it, is some value E, or we are sending a plane wave electron wave function whose eigen energy is E, and whose eigen energy is E. Now there are three possible cases. E is less than u naught, E is greater than or equal to U naught. Two cases, right? And classically, when this is the case, then the transmission, in other words, the electron will transmission will be 1. So it will be able to surmount that barrier. Classically, if energy is less than U naught, then the transmission will be 0. So if we plot the classical transmission, so I'm going to plot something called transmission. What is the meaning of transmission? Meaning of transmission is whether we'll be able to detect the ball on the other side. So if I was to plot the classical transmission, I'm going to use a little bit of a strange way of plotting it. I'm going to actually plot the transmission on the x-axis, not on the y-axis. Generally in quantum mech, y-axis is usually reserved for energy. Okay, and here we're going to make a mark of a point U naught. This is our U naught is our threshold. So if we now plot the transmission as a function of energy, pure classical, we expect it to do something like that. And transmission can only go from 0 to 1, obviously, right? So you cannot have, if I send in one ball, it cannot go, I cannot get two ball on the other side. So this is your classical transmission that we expect. Oh, sorry, I made a mistake. It's the other way around.
This is opposite.
Yeah, it's other way around. You're right. So 0 transmission I expect until U, and right after that I expect a 1 transmission. Now, when we do the quantum mechanics, I'll tell you what actually happens. So we get some very strange feature like this. Okay, it will not go above 1. When we do the transmission quantum mechanically, it will do something like that. Okay, so for very high energies, it will be very close to 1 only. So all the interesting things kind of happen, near energies that are pretty much equal to U naught. Around those energies, you can see the quantum transmission compared to classical transmission. It shows some interesting features, right? It shows some ringing kind of features. Okay, is everybody clear as to what is actually happening here? Classical black line, everybody understands. This quantum purple line is a little bit harder to understand. What is it? I'm giving you the final answer, right? Let us understand why this happens. Or let us say somebody gave you how this comes about. Let's try to physically interpret it. And we'll derive the purple line subsequently. Just wanted to give you a hint. Just some overall idea of the trailer for the story, rather, right? So what is actually happening here is that the quantum particle, even if its energy is below the energy of the barrier, total energy is below the barrier energy, it is actually able to, in some cases, go through. It has a less than 1 more greater than 0 probability of crossing, even if its energy is less. Not every time it will pass, right? If you pass it 100 times, maybe 60 of the times it will pass. But it has a non-zero probability. In the classical case, it's absolutely 0 probability. Okay, that is what we observe here. Okay. And if its energy is larger than E, then also there is no 100% probability that it will go through. No. Even if its energy is larger than the barrier energy, for certain values of energy, for example, certain values of energy, its probability could be less than 1 also. Which basically tells me that it has a probability of getting completely reflected by the barrier. Okay, that's what I'm telling. Okay, so this is where we are headed. Now let us go and see how this comes about. Unfortunately rather, we cannot. There's no analytical solution again for this. Okay, there is no way I can analytically derive and show you that this is the equation. So you have a homework problem where you're going to actually derive this purple curve. We'll set up the equation, do some interesting things with it. But the final plot, right, that you have to do numerically only using MATLAB or something like that. There you're going to get this purple plot. Today we'll set up the equations, and do the interpretation, all that. Great. So let us now set up this equation. Any questions until now about what I've presented, transmission versus energy and so on? Any questions
Sir,
on this?
classical one. That if energy is greater than or equal to U naught, then transmission is always 1.
Huh.
Yeah, if you first increasing gradually, then reach to at 1.
No, after even if it's energy, the moment it becomes larger then पार हो जाएगा ना, वो तो उतना ही है.
लेकिन सर ये कर्व फिर कुछ डिफरेंट जो क्लासिकल
नहीं, ये क्वांटम का ना, दिस इज क्वांटम, पर्पल इज
नो वन
क्वांटम,
ब्लैक वन
वो स्ट्रेट है, ऐसा ही है. Maybe I have not drawn correctly. Curve is like this. It's a step function only. Hello?
yeah, yes sir. But for here is this one is a straight line in between 0 to 1. If energy is from here to here is like
नहीं, देखो U0 से कम हो गया तो नहीं पार होगा ना, तो 0 है. U0 से ज्यादा है तो 1 है, तो क्या प्रॉब्लम है इसमें?
okay, yes sir.
ये discontinuity, this is a discontinuity ना.
Yeah, yes.
Step discontinuity है ना ये तो.
Yes sir. Thank you.
समझ रहे हो? This is a step function. This is step function.
Yes sir.
Okay. Any other question? Okay, we'll do the interpretation later as to why this happens and so on. Once we go through the solution, okay, then it will become slightly more clear. It will not become 100% clear in the sense that there is nothing you have seen in real life, okay, that does tunneling. Okay, so this is completely an alien phenomenon only. We'll never be able to, with our own eyes, we cannot see tunneling not happen. Okay, so it's abstract. It's something that is completely abstract. Okay, so I cannot give you that. Nobody can, because we cannot observe it in our daily lives. But mathematically, we'll try to see what is actually happening. It is much easier. Tunneling is much easier to understand if, rather than looking at electron waves, let's look at light, for example. Okay, let's look at light, and this much you have seen. So you can light also does tunneling. Let's look at light. In fact, what we're going to do, we're going to look at total internal reflection. Remember total internal reflection? If the angle between the rare medium was up, so it will come back total internal reflection, right? So if I ask people, and total internal reflection, what is there behind? Is the field completely zero? Then actually electric field is not zero. Electric field will actually exponent. There's an evanescent wave on the other side. Okay, there's an evanescent wave on the other side, right? So now imagine doing an optics experiment like this. I have a prism. I send a beam of light, and it undergoes total internal reflection. Then whatever comes in here, 100% of that light I'll get back. Okay, but now if we put another thin slab of glass here, okay, ऐसे लगा देते हैं. In fact, इसको ऐसा भी नहीं करेंगे, थोड़ा आपको we'll do a pyramid kind of thing only. We'll take another prism and we'll do this with the prism. Okay, we'll put another prism like this, and we start bringing these two prisms very close to each other. And if the distance between them is exactly 0, then all the light will actually go to the other side, right? And if the distance is exactly infinite, then 0 light will go. Now, if the distance between these two, if the distance is fairly close, and how close is determined by what is the wavelength. So if it's small enough compared to the wavelength, then people observe that under such conditions, the light, this will be not 100%. It will be around 0.9%. Maybe this light will be 0.1%. If these are sufficiently close, this gap is sufficiently small. This in optics is very well known. This is actually called frustrated total internal reflection. Very cool name, right? It's called frustrated total internal reflection. And frustrated total internal reflection is nothing but a manifestation of photon tunneling. Photon tunnels. Okay, so if you have problem with electron tunneling, and if you think, okay, ये तो हमको जिंदगी में कभी नहीं दिखेगा and so on, yes, you'll never be able to see physically an electron tunneling. That's simply not possible. You will see effects of it. You will see, if you build a device, you measure its current, you will see a tunneling current. That you will see. But physically you won't be able to see a photon electron cross. But if you do frustrated total internal reflection, this experiment you can do, well, not really in your hostel room, because this gap this we have to be able to control to a very small dimension. But at least we can do this experiment. It's called frustrated total internal reflection, and this is again a manifestation of tunneling. Here the photon actually tunnels from this prism to this prism. So there's a similar idea. So I hope that is somewhat clear. I just worry that maybe I have not confused you too much, right? So we will now set up the equations, set up the solution, and see what happens. So we take this barrier. This is 0, this is minus a by 2, this is plus a by 2. Height is u0. Okay. There is no trapped state here. Okay, there simply cannot be a trapped state. Why not? Because if the energy of the trap state is larger than this, then it cannot trap, right? If the energy is smaller than this, then also it can clearly leak out outside, right? So there is no trapped state possible. So that is the first thing you need to realize. If the potential is something like this, then immediately we know that there is no trapped state. Trapped state is simply not possible. So if trapped state is not possible, right, only states that are possible are propagating states. So immediately we know that here, in this region and this region, remember the solution can be a into e to the power I kx plus b into e to the power minus I kx, right? So immediately we know that in this region, this must be the solution like this. And we know that this is a forward traveling wave, this is a backward traveling plane wave. And I know that if I come in with an electron wave like this, there could be a possible reflection from this interface. And after that point, on the other side, there can only be a transmitted wave. There cannot be a reflected wave at this side, right? It doesn't make any sense. Okay, so on the right hand side, there is only a transmitted wave, and this is my incident wave. There will be a reflected wave. So there are 3 waves, and because there is an incident reflect, left and right are no longer the same, and so this problem does not have a symmetry. There's no left-right symmetry. So I have done here minus a by 2, 0 a by 2. ये सब करने की जरूरत नहीं है. It's not going to work out anyway, right? Because there is no physical symmetry. So in books, you will see that people will simply put a here and 0 here, 0 here and a here, because it doesn't matter, right? So we can do this also. Right? We can put a 0 right at the. Why did we do a by 2 minus a by 2? That is to use even symmetry, odd symmetry, all those things, right? But here the problem is not symmetrical. Left and right is different. On the left, I have 2 waves. On the right, I have 1. So there's no symmetry. So gone. Okay. So let us write this solution. On the left hand, we call this as region 1. We call the barrier region as region 2, and the right side region as region 3. In region 1, I can straight away write the solution of the Schrodinger's equation as ikx plus b e to the power minus ikx. Okay, I know that this is my forward traveling wave. So what I'm going to do is I'm going to simply take off this constant, okay, just to simplify my solution, because I know this is my incident wave, right? So, and then I'm going to take this guy here. I know that this is a reflected wave. So I'm going to write r times e to the power ikx here. So now r becomes my reflection coefficient. And I'm going to write also on the other side at region 3, say it looks like t times e to the power minus I k x, where t is my transmission coefficient. Now inside, what will happen? Inside, what will happen? It depends on whether my energy is less than u naught or greater than u naught. If my energy is greater than u naught, then the solution inside will be e into e to the power k2x plus b e to the power minus I k2x, where k2 is root of 2m by h bar square e minus u naught. Okay, if my, so this is less, I wouldn't say it's less interesting. In your homework, you'll have to do both. But today this is case 2. Okay, so case 1 would be, if e is less than, then my solutions are going to be of this form: e to the power plus kappa x plus b into e to the power minus kappa x, where kappa is a positive number, and kappa is going to be given by root of 2m u naught minus e by h bar squared. Remember, when we did this for the finite well, I said, okay, one of these constants will go away, but we cannot do that inside, right? Because inside, this is only true from x equal to 0 to a. None of these terms will blow up. None of these terms will go to infinity, so I cannot drop any of them. And so I can write for the, not the trapped states, when e is less than u naught, for those kind of states, or I would call them tunneling states, I'm going to write them as a into e to the power minus kappa x plus b into e to the power plus kappa x. Straight away, I wrote my final solution in this way. Now here, there is no, remember there is no trapped state here, right? Just to checking, everything is sound okay? And screen is okay?
Yes, sir.
Okay. So there is no trapped state here, right? Why is there no trapped state? You cannot be trapped. You cannot trap on a hill, right? How can I can trap you in a pit. I cannot trap you on a hill. I put you on a hill, how can it will roll down, right? So yeah, like that only. So because there is no trapped state, immediately we know that all energies are allowed, right? So there is no eigenvalue solutions here. Every energy is valid here, right? Every energy is valid here. Okay, so what is my only unknown? R and T are the only unknown. Really, R, T, A, and B, those are the things that we need to really worry about now to understand. More importantly, pretty much mostly we are really worried about this T. I want to calculate that particular T. Okay, so everybody got this, right? So K, small k and little k, they're just parameters, because energy can take any value. So for any given value of energy, question should be, what is the value of T and R for a given value of E? This is what this problem actually entails. Once we solve this, we are able to plot the purple curve. Purple curve is nothing but transmission as a function of energy. Okay, so let's see how it looks like. Okay, so now we have this equation, we have these wave functions. I have 5 unknowns. Actually, I have 4 unknowns. I have 4 unknowns, R, A, B, and T, because we have already normalized the incident wave. Okay, everything, all these proportions are with respect to the incident wave. That's it. They're just ratios. So we have 4 unknown ratios. So in order to solve them, I need 4 equations. How do we get those 4 equations? I need 4 boundary conditions. We have 4 boundary conditions because at each wall, I can enforce the continuity of the wave function and the continuity of its derivative. So 2 conditions at each wall of the barrier. So I have 4 equations, 4 ratios unknown, 4 boundary conditions. We're done, right? So let us write that. Let's write the first boundary condition. Let me cut it up. I need to have this cut up here a little bit. I hope the solution part is clear, right? How we are actually going about this. Should be clear to you now, right? So this is my wave function. So my first condition is, at the x equal to 0, I have phi of x continuous. Phi derivative of x continuous. At x equal to a, I have again phi of x is continuous, and the derivative of that is also continuous. So let us work it out, right, based on that. So x equal to 0 boundary between these 2 terms. So what I'm saying is r plus 1. So if I substitute x equal to 0 here, I get r plus 1 should be equal to a plus b. That's what I get from this guy. Then let's also differentiate. So maybe I'll do it a little bit more cleaner here. Let's also have the derivatives here, right? So this is my phi of x. Let's also have expressions for phi dash of x. So that is k into r into e to the power I kx minus, so I into k into r e to the power I kx minus I into k into e to the power minus I kx. This is, last one would be minus I into k into t into e to the power minus I kx. This one would be, kappa comes out, minus a into e to the power minus kappa x plus b into e to the power plus kappa x. So let me write the 4 equations now. I may be wrong in writing the equations, but I just want to give you a hint here. Okay, so first equation basically tells me that r plus 1 is equal to a plus b. Okay, that is yeah. So basically this equation and this equation at x equal to 0, equate them. Okay, so I will not do this for this. You got the idea, right? So the second one would be t is equal to no, not t. This one here, I'm doing the continuity. So that is t into e to the power minus ika is equal to a into e to the power minus kappa a plus b e to the power plus kappa a, like this. So these two equations, now we're going to write it in a special way. We're going to bring all the ABCD to the left hand side. So we can write the final equations like this: minus a minus b plus r plus 1 equal to 0. And the fourth equation, I can write it as minus a e to the power minus kappa a minus b e to the power minus kappa a plus kappa a. No, sorry, my mistake here. This 1 will keep it on the other side. Okay, so plus this yeah, it will be minus 1 here. Okay. Plus e to the power minus I k into a times t is equal to 0, like this. Okay, so I'm getting simultaneous equations, linear equations in a, b, r, and t. Okay, so you can do similar thing with the derivatives also. So I into k, I k r minus 1, I into k r minus 1 should be equal to kappa into b minus a, something like that, right? So I will not solve it. You should solve it. This is how we solve it for the case of E less than U naught. If E is greater than U naught, then this will be of the form A into E plus I k2 times x, where k2 is this number now. Okay, so you'll have you'll have a set of equations for E less than U naught, have another set of equations for E greater than U naught. In general, I can write these equations as in the following format. So remember, we have equations, right? 3x plus 4y plus 7z plus 8w equal to 3. Like this, you have 4 equations, right? In 4 unknowns. Similar like that only, this we can write it as some matrix, some 4 by 4 matrix into the unknowns x, y, z, and w is equal to some set of constants. 3, 0, 1, 1, whatever, right? So this could be 3, 1, 1, 8, 1, 0, 1, 3, 4, 1, 8, 1, 0, 0, 1, 1. This is a general linear equation in 4 unknowns. How do we solve this? Well, we solve it easily, right? The unknown matrix x, y, z, w is nothing but, if I call this matrix as A inverse matrix into 3, 0, 1, 1. Like this. This is how we solve for the linear equations, right? So then we get all these 4 numbers. Same like that is happening here. Okay. If you see this, I get 4 equations. Unknowns are A, B, R, and T. So after doing this, you're going to end up with something like this: A, B, R, and T. Okay, maybe I'll simplify this. So we have this matrix. Okay, there will be 4 by 4 matrix. Unknowns are A, B, R, and T. There will be some constants, and the first constant we already found out. It will be minus 1. So it will be minus 1 here. And how do we write this matrix? So for the first equation, what is the coefficient of A? It's minus 1, right? So we're going to write minus 1 here. And what is the coefficient of B? It's also -1. What is the coefficient of R? It's 1. What is the coefficient of T? It's 0. So this is how I write this equation in using pen and paper, right? And then what is the second equation? Second equation, a little bit more complicated. What is the coefficient of A? It is e to the power minus kappa A. So it is e to the power minus kappa A. Something like this, right? So all these terms, now either there'll be numerical constants or there'll be functions of K, A, and kappa. Internally, K and kappa are functions of U0 and E. So if you imagine now this matrix, the coefficients of this matrix will be functions of these numbers. So manlo A11, for example, it will be some function. It will be some function of U0, E, A, and H bar square, mass, these kind of things. Okay, so like this you solve this equation. I know it's may seem a little bit laborious, but this is a very good exercise. See, it's very easy observing me write these things, right? I've done it many times. In fact, this is the 5th year of running this class, so I've done it many times. So when I write this equation, it just literally rolls off, right? I don't need to think too much. It's like drinking water for me. But for you, if you just observe me doing it, it will look easier than it actually is, which is bad, right? We want things to, if it looks a little bit harder than it actually is, that's okay. But if it looks easier than what it actually is, you will say, okay, yaar, ye to main janta hu. Right? You'll be overconfident, which is not good. So that's why this exercise is given in the homework to make you derive this, right? And so I hope you understood, right? You'll get an equation here like this, which will be functions of constants will be K, A, and kappa will be there. So once I do that, I'm going to. So if I give you the value of E, I give you the value of U0, I give you the value of A, everything, then you can ask the computer, it will simply give you a numerical value, right? And so you can go to MATLAB and simply do inverse of the matrix and multiply that by this other vector, right? So end of the day, you will get numerical values. So for any value of E, you will be able to get R and T. Now, if I do T, if I take absolute value of T squared, that will give me capital T transmittance. So this is how you will be able to plot T versus E. And you should be writing a separate set of equations for E less than U0 and a separate set of equations for E greater than U0. Ultimately, let me show you. Is this clear? Any questions about this? I hope I'm not confusing you totally. So if you look at Wikipedia tunneling page, that plot is there in that. Okay, so quantum tunnel. Yeah, so you can see this plot. There used to be another plot. I don't know whether it is still here. Yeah, I mean, it should be there somewhere. If it's not there, you can observe it later. There used to be a plot of E versus T, but doesn't matter. You can also get it. Let's see if there is any plot here, which is. It's not there. Okay, no worries. You solve it. I'm sure you'll be able to find it as well. But it will look like this only, like purple line what I've drawn. It will look like this. So at E equal to U0, you will get a non-zero value. It will be a nice continuous value. Okay. pretty much t is going to be proportional to e to the power minus u naught a, everything will be there. Okay, so it will be related to these things. Okay, so this is one homework problem which will involve you first of all completing the right equations properly and generating that matrix, and you will write a code. Okay, so e varies from, you create an e varies from 0 to, I don't know, maybe 3 times u naught or something like that, in steps of 0.1, whatever, 0.1 u naught or something like that. For every value of e, you're going to generate the value of k and kappa, and based on this you're going to then complete that matrix. Then you're going to invert that matrix and multiply the constant matrix, and you'll get values of a, b, r, and t as a function of e. So then you will be simply do plot e comma t squared, or in our case we should actually put e on the y-axis, so you're going to plot t squared comma e, something like this. Okay, yeah, I hope the assignment is clear. Work it out, you will get it. Now let us go to the interpretation of tunneling. Okay, the interpretation of tunneling, and that is what you'll find in some of these images that we saw. So the input wave at any instant of time is going to be something like that, and the output wave is also a propagating wave. In the middle, now you'll have some function like this, mathematical function like this. Okay. Once we are able to solve for a, b, r, and t, a, b, r, and t, let's say we are able to solve what is a, what is b. Now you can go to my wave functions here that we have written. This set, right? This set. Once I know the values of r, a, b, and t, remember I already know k and kappa, right? So you can substitute this equation, and you can have a, if you want to visualize it, I highly recommend it. If you want to visualize it, you can definitely plot phi of x, absolute value phi of x squared versus x. Okay, and you'll then be able to visualize what is the probability and so on. So it'll be a very nice exercise to do this, but this is not there in the homework. This is for your own learning if you want to do it. Okay. So what is the physical interpretation? Physical interpretation is very similar to this frustrated total internal reflection that I talked to you about. There is going to be this is your evanescent tail. Whenever I have a wave that if a wave function hits a barrier, because I need to ensure that the derivative is not and the wave function are continuous, and because the potential is not a delta function, by necessity there has to be a tail. Okay, and by necessity there has to be a tail, and this tail also cannot go to 0 here, so that tail will result in another wave that comes in on that. Okay, so tunneling is a result of geometry. Basically, remember we derived the condition that the slope and the wave function both have to be continuous at every interface unless and until I have a delta function. So if you have a non-delta function potential, because of the mathematics of the Schrodinger's equation, by necessity, the wave function has to exhibit continuity of slope and wave function itself, right? And because of that, actually, we have tunneling, right? So that is the reason why we have tunneling. That's a mathematical way of looking at tunneling. There is no other way, to be honest with you. If people can give you some other explanation, there is no other way. In my opinion, it is initially we say, by some experiments we say that wave function has to satisfy Schrodinger's equation. That much we saw, right? And that has to be true, because once we conclude that electrons must satisfy wave function, then we go ahead into use that equation and solve for atoms and spectra, we get correct answers. So we decided that yes, wave function has to satisfy Schrodinger's equation. And if you now tell me wave function has to satisfy Schrodinger's equation, then by necessity it has to also lead to tunneling, right? So tunneling is a wave property. Tunneling is only done by waves. Particles don't tunnel. So if you ask me why do the electrons tunnel, well, the answer is very simple. It's because they have wave-like properties. They did not have wave-like properties, they would never tunnel. You and I, we have wave-like properties, but very minuscule amount of wave-like properties. Our wavelengths are very long. They're extremely long, right? P is equal to h by lambda. But lambda is h by p. Your momentum is quite small, but h is even smaller. So your lambdas are, lambda is very, very small, not large. So lambdas are very, very small. Your lambda and my lambda is very small. So all the physical objects that we see in our world, they are much larger than lambda. They're very large compared to lambda. And because they're very large compared to lambda, we don't see any tunneling effects in classical objects, you and I, for example. Right? So the other interesting thing I want to tell you is the wave-like properties, right? So wave-like, and this is, you may not have thought that this is all same, right? But it is. Remember, when you're doing optics, we learn about geometrical optics, wave optics, and so on, right? So geometrical optics is true when the size of the object is much larger compared to the wavelength. So glasses, for example, I'm wearing a glass, you're also wearing, if you're wearing a glass, the size of the glass, the size of the lens of the glass compared to the wavelength of light. Wavelength of light is that my eyes can see is around 400 to 800 nanometers. Size of the glass is centimeters. And so in that case, light also behaves almost like a particle, right? Light behaves like a ray optics, geometrical ray optics. Same thing is happening in our day-to-day life also. The wavelengths are so small and the objects are so large compared to it. Our door size, the size of the door, size of the wall, size of the buildings, they're much larger compared to the de Broglie wavelength. My de Broglie wavelength, your de Broglie wavelength. And that is why we don't exhibit any wavelength. We behave like particles. Okay. So I hope this is clear to you. I hope this, the depth is clear to you, right? Wavy properties. Electron has both wave property and particle-like property. That is why it shows, and photons, for example, very low wavelength photons, for example, radio frequency photons, the very large, long wavelength photons, they almost never exhibit any particle-like property, because their wavelength, if you compare to the world we are living in, if I send a radio wave, its wavelength is kilometers or even thousands of kilometers. So according to it, every object is much smaller than the wave, right? So then that will behave like a wave only. It will not have any. So let me write this observation here. So compared to any entity, it has a characteristic wavelength, and for particles it is the de Broglie wavelength, and it is going to be there in a universe, right? Maybe a room or a size of your device or whatever. So you need to compare whether the size of the device, is it much larger compared to the de Broglie wavelength? Is it much smaller compared to the de Broglie wavelength? or is it comparable to the de Broglie wavelength? And so if it is much larger than the de Broglie wavelength, de Broglie, if you really want to be specific, you call it de Broglie. So de Broglie wavelength, then here we have a particle behavior. Particle behavior. And if it is much smaller, the device length is much smaller compared, then here we have a almost exclusively wave-like behavior. And if it is comparable to the de Broglie, this is where all the interesting physics happens. This is where you will see wave particle duality. And it so happens that, electrons kind of occupy this interesting regime. For the most part, photons are kind of occurring here. Well, not the geometrical optics, the wave optics photons, right? So it would do interference and so on. So they're, or you can say very low radio frequency photons are occupying this region. And human beings, compared to our de Broglie wavelengths, we are somewhere here. Our rooms, our doors, all this is here. Almost exclusively particle-like. And photons, right? Visible wavelength photons, they're also in this sweet spot. They're also in the sweet spot where they're also closer to their characteristic wavelength. So they're also close, yeah. Okay. So you can observe very interesting effects. You can observe wave particle kind of effects, especially for X-ray photons and so on. Okay. So I hope this is clear. I hope the idea of tunneling is clear to you. So let me summarize what all we have discovered by solving the Schrodinger's equation in a one-dimensional potential. We have gone from an infinite well to a finite well and its opposite to a finite barrier. And here we also talked about multiple barriers. What happens in a multiple barrier? What happens in a multiple barrier? We have degeneracy splitting. We have band formation. Now the question comes, okay, what happens if I have multiple barriers, not multiple holes? What happens if I have multiple barriers? This is a very interesting question. If you have multiple barriers, then also we have again band formation. This is what leads to semiconductors, insulators, band gap, all that physics comes in from the presence of multiple, especially when these barriers, multiple barriers, are all arranged in a periodic fashion. That is when we have all very, very interesting physics happening. Even if they're not periodic, then also there is a lot of interesting things happening. Okay, so disordered crystals is very interesting physics happening there. We have something called Anderson localization, very interesting physics in disordered barriers also. Okay, matlab the barriers are not arranged in a periodic fashion, they are arranged randomly. Then also very interesting physics. But it is difficult to solve analytically. And it's very difficult to understand the theory of scattering in multiple scatterers. So after doing this, usually traditionally quantum mechanics goes into solving the problem of multiple barriers, but in a periodic multiple barriers. This is where we go next. This is where quantum mechanics usually will go next. Okay, but I wanted to do something else. Let me say. Yeah, so sorry, my mistake. Yeah, this is where we're going to go next, right? And this is where we're going to understand insulators and band formation, effective mass, everything comes from that, right? So you see the logical progression here, right? We started from no barrier, u of x is 0. We know that, continuous eigenvalues there. Then we went to the infinite potential well, very simple to solve analytically. What we realize is anytime we have trapped states, we're going to have eigenvalue discretization. That is the very word quantum, which comes in quantum mechanics, right? Yeah, that is why quantum comes in. Discretization happens when there is a trapped state. Okay. After that, we moved on to I talked about multiple wells. What happens with multiple wells come together, energy splits. There you have formation of bonds, chemical bonds, and so on. After that, I again talked about scattering states, trapped states. Then I went into solving the scattering state from a single barrier. Okay, so I hope all this is kind of sitting in your head well. And when you solve the first homework, hopefully this will solidify a little bit better. Before going into the multiple barrier problem, which is very interesting, trust me on this, we're going to, I'm going to just talk to you about tunneling from two barriers. Okay, this itself is very interesting. So, in fact, this is tunneling two barrier, right? So we have a two barrier problem. And I said this is very interesting. We have devices also. These are called resonant tunneling diodes, RTD. And people were very hopeful of this, but promise has not really panned out. Okay, there are some issues with that. But anyway, people are very hopeful of these devices. So let me take you, before going again into the mathematics, let me take you into the world of devices now. And let us try to put whatever we have learned in this mathematics. Let us try to put it in the context of a real device, right? Remember, in real device, when we draw a well like this, right? In reality, we can never realize something like this, right? Because how do we realize a potential well? You have to use it using atoms only. You have to build these things using atoms. And so, we cannot realize these abstract kind of shapes in real life. If somebody tells me, okay, make me a finite potential well, it's not possible. Simply not possible, right? So how do people build these kind of potential wells and test things, right? So let me tell you about that. One interesting way in which people initially started working on this was by using something called as heterostructures. And specifically, they were working on something called semiconductor heterostructures. And this work happened from the 1960s to 1980s mostly, and now also it's going on. Okay, now also there's very interesting things going on. Well, I'll tell you about that. So what were these people doing? They were trying to build, everybody knows about potential wells and so on, right? So they were trying to see whether they can build potential wells in real life and observe this quantization effects and so on. And how did they do that? This is how they did that. So it was all made possible by depositing multiple semiconductor materials one on top of each other. So I'll basically take some semiconductor crystal growing technique. I'm going to grow one semiconductor here. I'm going to call it semiconductor 1. Example, this could be gallium arsenide. Okay, so usually these are 3-5 semiconductors, and I'll tell you the reason why we go for 3-5 semiconductors. So they do this gallium arsenide. After that, they're going to grow on top of this a second semiconductor. So they deposit a second semiconductor here. this is your semiconductor 2 or layer 2 if you can. Usually this is going to be a material like aluminum gallium arsenide, and they don't really grow this. Rather what they do is they kind of dope. If I take gallium arsenide and I dope it with aluminum gallium arsenide, dope it with aluminum, you got aluminum gallium arsenide, you got a second semiconductor. After this, what they do again is they're going to deposit again one other semiconductor. Usually this is going to be the same conductor as before. So this is going to be S1 only. It's going to be again gallium arsenide. It's going to be gallium arsenide again. So now if I cut a path like this, imagine an electron that is traveling perpendicular to these devices like this. Then I have not talked about band structure and so on, and I'll talk about it in detail later on. But for now, I'm sure everybody knows about band structure, right? So I'm going to borrow from your knowledge of semiconductors. So first semiconductor will look something like this. Okay. Gallium arsenide or some other aluminum gallium arsenide, this could be the other way. It'll have a different band. So this is my S1, this is my S2. This is my S1 again. So if I'm going this way green, right? I'm going from semiconductor 1, going to semiconductor 2, then going to if I literally walk from one place to the other place, what is the combined band structure? It is slightly more complicated than what I'm drawing here, but essentially it will start looking like this. Okay, so it will start looking like this. Well, sorry, my mistake. There'll not be a well. Down below it will be like this only. Well, in the valence band, there will not be another well. See, because this is height, this much is height here, not this much height here, and this is chota's height here. So if I adjust it, and I'll tell you precisely how we do this, draw it properly, and we'll do it in detail later. But if I put them together, the essential final band structure will look like this. Now you see what has happened. Now I have gotten this is your quantum well. It looks like a well, right? And you will have these eigenstates forming here. Okay. And now when you apply a potential and so on, you'll have very interesting effects. So for example, the difference between these two levels, the material will absorb a lot of those particular photons. And so you have a very efficient detector, for example. So yeah, right. And what is the other nice thing? Other nice thing is, using this procedure, it is now totally within my capability to adjust this. I can adjust the width of the well. How do I adjust the width of the well? By adjusting the width of the layer thickness for the second layer. I've adjusted the width, right? Width of the well. How do I adjust the height of the potential barrier? That is by the amount of doping that I do. So the larger, in fact, if I, okay, I'll tell you. So this is gallium arsenide. And on the other hand, I have another semiconductor, aluminum arsenide. Now I can have different kind of alloys. Gallium X, aluminum 1 - X, arsenide. So for example, I can have X equal to 0.5. So I can have gallium 0.5, which is a half mixture of 50% alloy between gallium arsenide and aluminum arsenide. So I can literally control that X, right? I can go from, you see the beauty here, I can control it from X equal to 0, which is pure gallium arsenide. I can control it all the way to X equal to 1, which is pure aluminum arsenide. I can control the alloy ratio. This is actually called stoichiometry. I can control the stoichiometry of this alloy, which is just controlling the X. Okay, that's called controlling the stoichiometry of the alloy. I can control the stoichiometry of the alloy, and based on that, this will have a different band gap, this will have a different band gap. So depending on the stoichiometry, I'll get a band gap that is somewhere in between gallium arsenide and lithium arsenide. And so I have now able to precisely control the barrier height as well. And I'm precisely controlling the barrier width as well. And depending on the effective mass of the electron and the thickness of this material and thickness of the barrier, stoichiometry of the alloy and so on, people were able to realize different wells that we just talked about, right? And so why is that interesting? That's because if I control the width of the well, everything, I can precisely control values of E1 and E2. I can control where E1 is. I can control where E2 is. If I control E1 and E2, I can also control E2 minus E1, right? So I can pretty much by design, I can design any value of E1 and E1 minus E2 that you want. Remember, any photon, electron will be here. If it absorbs a photon, it will go up here, right? So if I design E1 E2 correctly, then I can design it to absorb any particular photon frequency. So I have designed a precise absorber. I've designed a photodetector at a very specific wavelength. Now, this was a huge deal, and I'll tell you why. Because they could do this for infrared. Okay, so this is your thermal, right? So they could do this for thermal wavelengths. And the moment they did this, this is where they had thermal cameras, and they could do very specific missile detectors, or not missile detectors, but actually heat detectors. So they could detect when an object has a slightly higher temperature than surrounding. And I put this detector on a missile head, boom, right? Here, they can specifically detect persons and only target that person. Only target bunkers where there are human beings that are living. So this is how, literally they could bomb camels, caves and so on. This is the technology, right? So that is why this was very huge. And lot of money flowed from defense. But now this is great. This is very good research, because people did a lot of basic research in how to, in the optical properties and electronic properties for all kinds of compound semiconductors. These kind of semiconductors are called compound semiconductors. And that research really paid off well. And especially whenever you do compound semiconductor based devices, you always either use a quantum well, or you use a quantum wire, or you use a quantum dot. Okay, this quantum concept is absolutely essential in designing compound semiconductor based devices. And gallium nitride, everybody would have heard, right? So gallium nitride is a compound semiconductor. First work started in gallium arsenide. Then they wanted to shift it to gallium nitride because it has larger band gap, and so on. And that research has now led to huge revolutions in LED, right? LED research. So we have white light LEDs now, and pretty soon all our energy needs in the entire world are going to be replaced by gallium nitride based white LEDs. Highly efficient. Nearly, they're going to shoot for more than 50-60% efficiency lighting, whereas fluorescent lighting is only 8% efficiency. Right. So you see what there is a relationship between very basic level understanding of quantum wells, for example, solving it in a finite potential well, and you see the device implications of that, very amazing implications of that. And this is what they have done. They have done lasers out of this. They have done thermal LEDs, thermal photodetectors, everything. All those compound semiconductor based devices are all based on this idea of a semiconductor heterostructure. If you understand finite quantum wells, If you understand the solution of Schrodinger's equation of finite potential well, you understand a lot of compound semiconductor devices and technologies. Yes,
I have few questions.
please
Yeah.
go ahead.
Yeah. First is, sir, why this valence band is flat?
Well, how to draw that exactly? Now we will look at it later on. Okay, because I have to cover some other. Sometimes you can have where the well appear in the valence band also. Sometimes it will appear in both the valence band and conduction band. Depends on exactly how the what the values of these bands are and so on.
Okay, sir.
Okay, that's a good question. Hold on to your curiosity. When we move on, when we in our later section, when we'll spend a lot of time in drawing band diagrams for many cases. There, your curiosity will be answered.
Yes, sir. And sir, second one is, why we choose only 3/5 material?
Okay. There are two reasons for that. One is this. One is this reason. So remember when we go from one material to the other material, the material will have a lattice constant, right? So, if that lattice constant is very different for these two semiconductors, then you'll not have a good addition. तो आप deposit करोगे वो धूल जैसे उड़ जाएगा.
Yes, sir.
Continuous crystal, this interface will not be perfect. Okay, and so it turns out that for our 3-5 semiconductors, especially the gallium arsenide, aluminum arsenide system, that has a very decent lattice. It does not have any lattice mismatch problems. Okay, so if you go to silicon and silicon germanium, there is a lot of problems. Silicon and germanium usually don't have same lattice constants. So you cannot make heterostructures with lattice mismatched semiconductors. So if you want to do heterostructures, you have to go to material systems where lattice mismatch is not a big problem. Does that answer your question a little bit?
Yes.
It's based on trial and error. Okay. So first of all, if you look at the periodic table, we have a few elemental semiconductors. And those are your silicon, germanium. Those are your elemental semiconductors, right? Most of the elements are metals. A lot of them are gases. Most of them are metals. A lot of them are gases. And only few of them are elemental semiconductors. Okay, so your choice of element semiconductor is limited by that. And so the next best thing is to go. Silicon is 4, right? Silicon is 4. It has 4 electrons around it. Right? So people figured out if we take a 3 and a 5, which will also add 3 plus 5, karke aapko 8 aega. So they figured out that 3 and 5 alloys also are semiconducting. And so they started working on this. And luckily, they figured out, they can make very pure 3-5 semiconductors also. They literally grow it. How they grow it is, they take a piece of gallium metal, they take a piece of gallium, they take a piece of arsenic, and usko overheat karte hain. So they heat it, then you have gallium vapor, you have arsenic vapor. Then they put a glass plate and they catch that vapor. Okay, so that vapor will condense and it will give you a very pure semiconductor. So they grow it atomic layer by atomic layer. Okay, so that is a second reason also, is because we can grow these compound semiconductors very nicely to very high purity. You can make but they are expensive because of that reason also. They're more expensive than silicon. Silicon kya hota hai? You just take glass, you just take sand, and you literally keep on heating that sand. That is how you make silicon wafers. Gallium arsenide and these things, you literally grow it one atomic layer by another. A little bit more information than you asked for, but I hope that answers your question.
Yes, sir. And sir, one more question. Sir, gallium nitride has a high mobility. And yeah, I have read somewhere because this high mobility because of this quantum wave.
Okay, gallium nitride. See, mobility is a little bit more complex thing. Mobility is dependent on how pure your material is. Okay, and remember I told you compound semiconductors, we grow it atomic layer by atomic layer, so we are able to get high purity, very high purity. That is one of the main contributors as to why there is high mobility in compound semiconductor devices. Okay, because there is less impurities, right? That's only one of the reasons. A second reason is that which we have not studied yet. That is due to effective mass, and the effective masses for electrons in compound semiconductor is very low, so they're very light. Okay, so we have a pure material plus we have low effective mass, and so the mobility is high. Okay, so mobility pe abhi nahi jayenge, it's more complicated. We haven't covered the concepts yet, but band gap in gallium nitride is definitely high.
Yeah, thank you, sir.
Thank you. Any other questions from other people here?
No, sir.
Okay, there is no question. I think we can go forward, but we are almost closing time. So I'm going to stop here. And homework has been posted by Monica. So I request people to start working on it. It will be due 2 weeks from now. The homeworks in this class are somewhat heavy. And the reason is we only have 4 or 5 homeworks throughout the entire course. So these are like small projects in a way. You can consult your classmates but I highly recommend that you try to work it out on your own to emphasize these concepts. Monica will be able to help you if you need any problem, need any help with coding or something like that. She can give some help. Okay, and that is all for today. Thank you very much.